Okay, yesterday we left off with the idea, probably the most important concept would be the difference between distance and displacement. You put there, young man. Yours is 26.
Yeah, down there. I got it.
I mean, it's no big deal. Yeah, you might want to try to get the same book that everyone else has, but if they don't leave the room, it really should not make any difference. All this note card is saying is if you check out number 15, it's been issued, you're the one that checked it out, that number 15 has to be here next spring, unless you pay the fine for it. Does that make sense? How many of you plan on taking a book out of this class? Which is fine. It's not that big of a deal. Okay? I mean, it doesn't mean that just because they're found here and there's a shelf that they have to stay here. No? That just gives you the luxury of lighting up, not lighting, lessening the load in your backpacks. Okay. So, yesterday, distance and displacement. What might the difference be between a distance and a displacement? The example we gave would be the distance from home to second base on a baseball field. Because when you travel in baseball or softball, do you go straight from home to second? No, you have to go around first and then to second. So, if it is in baseball, how many feet is that approximately? If it was a straight line distance from home to first and first to second? It would be 180, but that person's probably not going to travel that 180 because, as you said, you might round first base. Okay? So, that then is a distance that has been traveled. But the displacement then is not 180 and it's not 200. It would be the distance between home and straight away to second base in a straight line. Is anyone confused with that logic? I'm going to write it down anyway. Okay? So you can go back and hopefully it might make sense with this. Okay? So here's our baseball field. Okay? Kind of looks maybe a little bit like a snow cone. Okay, so here's home base or home plate. Here's first, here's second, here's third. Okay, so we know the distance between each base is 90 feet. This is 90 feet. 90 feet here, of course, 90 feet here. So when a person leaves home plate, they are probably traveling, like you correctly said, maybe round first, then go to second. Okay? So we know that this is 90 feet, that's 90 feet, but this extra little bit we're going to say is 15 feet. Okay? So when we add these together, 90, 15, and then another 90, which is what, 205? 195. 195. Is anybody just totally lost? Okay, so this is the distance that was traveled, right here. The displacement from where you started is this distance. It's just a straight line from where you began. That is this dashed line here. And that's where we get the idea of that Pythagorean theorem. So whatever that is, let's see here. 810 plus 810. Just do it like that. It's 8100. Correct? My math is a little bit off. But what's 9 times 9? 8100. So when you take 90 times 90, you get 8100. 90 times 90, you get 8100. So then this distance we give you, you're not going to have to do this type of math. We're just using this as an example. So don't let that be so over intimidating that, oh my gosh, we're doing trigonometry in here. No. No, we're not. We're just using this as an example. So when I was in college chemistry class at Worthington Community College, probably the chemistry professor that got me interested into maybe teaching. I was going to be a respiratory therapist. I decided to go into education. His saying was, instead of saying, "Do you understand?" that you're on the bus. If you're on the bus, that means you understand. So ask some of your older brothers or sisters, they're going to say the same thing. You said, God, he asked if we were on the bus today. You should know what that means. So typically what we do is when we go over these, I'll say left outside. Are we on the bus? And that means this is yes, like Mr. Hammer says, this is no. So left outside, are we on the bus? And I do not move on until I see responses. Are we on the bus? Left middle, are we on the bus? Middle, are we on the bus? Right middle. And right outside. Right outside. Okay. At least move. This is yes. This, you see how little I can move my head. This is yes. This is maybe. This is no. Right? So one of the aspects that you can do is, if you don't understand, we talked about this yesterday. One, you can come in and talk to myself. That's probably further down the list. Number one is probably talk to one of your friends or classmates. Number two is find an upperclassman and ask them. Probably number three is looking at this video again. Maybe number four is coming and talking to myself. Now you can prioritize those how you choose, but you have this technology to help you. Okay? You need to make that decision. If you need help, you need to ask for help. I'm just grading you and evaluating what I see in front of me. Like it, don't like it, but what did we say yesterday? You want to be treated like young adults, you have to have that responsibility. Or would you rather have me be a helicopter and move all around and say, Haley, you got to be doing this right now? Is that what we want? Would you rather be, okay, got a little bit of freedom here. Option one, where I hover over you, or option two, you get a little more freedom? Is it one? You're nodding your head yes. Okay. You want option number two. You get a little more freedom, and you people, you're responsible. You're in high school now. Okay. All right, fair enough. So then the distance between, or excuse me, the difference between distance and displacement is how far you are away from where you started. Okay. You may have traveled a little further than what your displacement is. But again, those are the differences. And those are your vocab terms for this chapter. Okay. So this is where we left off with a rate. You need to get through your mind if you see a number labeled in meters per second. You need to know, what is that label? What variable? Oh, maybe I'm back. Sorry. Something is labeled in meters per second. That is what? Speed or velocity. Remember, speed is labeled in this, but velocity is just telling you 20 meters per second east. Okay, that's a velocity. Sometimes these stored problems may say it has a velocity of 15 meters per second, or it might say it's got a speed of 15 meters per second. Just get it through your mind that speed and velocity are very similar, since velocity is a specific direction. Okay. Can velocity be negative? No. It might slow down, but it's always going to have a positive value until it reaches what? I went from that side of the room to here and did what? Stop. Does it have a value for velocity? No, but it's still not negative, is it? Yeah. All right. So as we move on, acceleration then. So just like our hot chocolate example with temperature, objects will either speed up or slow down. Objects either heat up or cool off as well. There's no such thing as negative heat. It just means that heat is being released. There's no such thing as negative velocity. It just means that an object is slowing down. Speedos today, isn't that the best item on the lunch menu? Who says yes? Really? I never would have guessed it. I thought you would like the Speedos. Is it chicken fajitas then? Is that the nuggets, huh? Okay. That's surprising that you would like this. Okay, that's what makes us diverse. Not everyone likes the same thing. All right. So one more, and then we will go ahead and we got a couple story problems to go over. And we'll get to this in just a moment. You're going to want to make a formula sheet. Probably in a notebook. We don't want you to write any examples on your formula sheet. And to me, if you choose not to write these formulas down, is that because a person's lazy, just chose not to, or don't care, or one or the other? Because I think it's important that you have these formulas and that you know how to use them. Okay? So what I would suggest, you've got that entire back page, or page 4, it's blank. I wouldn't use that as your formula sheet, but you may want to write these story problems down, or in a notebook, or wherever you feel most comfortable with, or wherever there is space provided. Because when we get into the spring semester, how many of you know anything about the periodic table of elements? Okay? Do you have to memorize some elements? No. It's more important to be able to know how to use that than it is to memorize it. Of course, if you wanted to, you could go hydrogen, helium, lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium. Then you're up to 12, then you're going to go over to aluminum, that's number 13, then the silicone, then the phosphorus. Phosphorus is 15, 16 is sulfur, then 17 is chlorine, and 18 is neon. See, you get really good at these, then you memorize. Because what we could. What's that? What did I say? Neon? Oh, that's 10. So if we really wanted to, we could say, wow, it is sodium zinc time right now. What element is sodium? Number what?
11.
11. Zinc is what element? 30. Hey, it's sodium zinc right now. Pretty cool, huh? You learn something every day. Now, every day that's 11:30, you're going to think of sodium and zinc. No? No? Fair. All right. So what we want you to do now, okay? We have another formula. Okay? Don't worry about the very top line. That's organic chemistry. Okay? Because we keep referring back to that. So you have two formulas. You can say velocity or speed. I suggest that you write these down. Again, we just had that discussion. I'm not going to go walking up and down and say, no, you really need to be writing these formulas down. You should be doing that anyway. All right, so velocity equals a distance over a time. Okay? So if that's the formula, the labels for those would be as follows. How do we measure speed or velocity? In what? Meters per second. And again, get that through your head. I'm putting in parentheses what the labels are. Meters per second is a velocity. Okay, don't get that mixed up with the formula. We're just saying that velocity is measured in meters per second. So just write down what you see in the orange. And if you need to write the labels down somewhere else, you're more than free to do that as well. All right. So now, distance. So what do we see here in this story from? A speed of 7.71 meters per second. What does this meters per second tell you? You are having this number is what variable? What does it tell you? Speed. So therefore, it belongs over here on this side of the equation. That's why we want you to get that terminology down so you can understand where these go in your formula. Okay? So, the top portion. What does the M stand for? Meters. Meters is a what? Say that again. It's a measurement. So it's telling you how far. Okay? So our distance then is measured in meters. And time is measured in what? Seconds. Now, are all speeds and all velocities measured in meters per second? No. You hop in your car and you got these two labels you could use. Miles per hour or lesser known kilometers per hour. Okay? So if we see something measured in meters per second, we know that it's a speed or a velocity. If something is measured in meters, we know it's a distance. If we see something measured in seconds, we know that it is a time. All right? Left outside, are we on the bus? Yes? Okay. Way back corner, left outside. Okay. Left middle. Middle.
Oh,
See, now that's what we like. See, it's not only saying that I'm on the bus and I understand, it's I'm having fun too. Is that true?
yeah.
You wouldn't lie to me, would you?
I said
Not really.
Yeah.
Okay. I'll put what I want to say, a spy on you. His name is Brady. See, you're an intimidator, right?
Yeah.
Oh, it's just Brady. Right middle. Are we on the bus? Right outside. Okay? Well, for some of you going like this or like this, you may just, yeah, it's going to take a little bit of work. A little hard work isn't going to hurt anybody, is it? Where I learned that phrase was from a gal, I believe her name was Mrs. Carson. Her son was better known as Ben Carson. And Ben Carson was the head of, over in Johns Hopkins University, the head of neonatal neurology, I believe. Okay? Very, very smart man. And his mom told him a little hard work isn't going to hurt anybody. Okay? That the world is full of everybody else. What does that mean? You just need to be concerned about what's in front of you. Don't be concerned about what your neighbor's doing. The world is full of everybody else. Okay. So, our other formula that we just covered was what? What did it say? And if some of you are intimidated, my apologies, but you're just getting used to this. Okay? It doesn't have a reflection on your intelligence. It's not better than junior high. It's not worse than junior high. It's just a little different. Okay, so the very last thing that we had wrote down was acceleration. So what is the formula for acceleration? Okay, so it said something like the acceleration. So we're just going to say A for acceleration. And then what did it say on that line? Final velocity minus okay. We're not really okay, acceleration equals final velocity. What's this? What do you suppose it means by initial? Yeah, where it happens first. That's your first velocity, so initial velocity all over what? So this is a dividing sign, just like what this one is. So what variable goes on the bottom? Time. Okay? So very, very important. You've got to get this. Well, not you've got to. I really, really want you to understand this. Okay? The difference between the labeling of these two variables, acceleration and velocity, they both have meters over seconds, but we briefly said yesterday something specific about the second. It's what? Not cubed, but squared. And how do you denote something is squared? Put an exponent of what? Everyone catch that? 2. So when you do that, meters per second squared is not a velocity. It is an acceleration. Okay? We already know, how do we label velocities? So it's what over what? Meters per second. How you label this one? Meters per second. And how do we label time? seconds. Okay? This is where, on the first day, we asked, how many of you like math? So how are we doing so far? Maybe we don't know yet. We just had formulas and variables, and we're about ready to take our first step in solving math problems. How many of you are going, yay? Nobody. Okay, away we go. We're going to do the bottom problem first because that one's probably a little more simple. Okay, so what we want you to do is this will help you out a lot if you do and solve these problems the way that we show you how to. It will definitely help you out a lot. Please take that piece of advice. Okay, so it says a tiger closes the gap in the kill zone. What that kill zone means is that these types of predators, if they are not successful in their hunt in that kill zone with a certain amount of time, that deer or gazelle or whatever's, once it gets past that kill zone, what's going to happen to the distance between the two animals? It's kind of like I'm the tiger every day in cross-country practice. I'm a very hungry tiger. I'll probably stay a very hungry tiger. Why is that? What's the distance doing? It's getting further and further ahead. I can't keep up with it. But that's good. That's what I want. I don't want to catch anybody. And I haven't yet. There's no reason to say that I would or could or should. Okay. So a tiger closes the gap while hunting in this kill zone on a deer in 2.15 seconds. That's an S. So the S, what is that telling you? What variable is 2.15? It's a time. So this is what we mean. We want you to solve these problems in the way that we're illustrating. We call this a setup. The time is equal to 2.15 seconds. Okay? Then, what other bit of information does it say? This distance was 52 meters. Okay? So M is labeled in meters, so that is what variable? Distance. Right. Okay? So our distance, 52 meters. Okay? So what is the question ultimately asking for here? Speed. And we know when we calculate a speed, it is labeled how? Meters per second. So speed is our variable of velocity or speed, and we don't know what that is because that's what it's asking for. What is the speed? Or it could say, what is the velocity? Okay? So the important part about that is once you have your setup done, you don't have to go reading through the entire problem again. You can just look at this and say, okay, I know my time, I know my distance, I need to find this variable. There's nothing worse than reading a story problem 3 or 4 times and I don't know what I have. But when you do this with a setup, now you know what to do. We hope. So do what the formula tells you to do. Velocity equals what? Distance over time. So what was our distance? 52. What was our time? You don't need to put the labels up here because you've already accounted for them down there. So we do what the formula tells you to do. What do we do with those two numbers? Divide them. Okay? So when you do that, Do you get 25? It's got to be pretty close. Okay, so the velocity equals 24 to 2 decimal places. We want to go to the nearest hundredth. 24 point and 2 point. So that'd be 2 there. Could you say it's 2, 1? What's the next number after the 1? Okay. $24.186. So what that does then, you did say 19. I thought you were telling me that's what the calculator was saying, not what the answer was. My apologies. Okay, so now we got our answer, 24.19. How do we label that? Meters per second. Okay. All right. Are we on the bus so far? I'm not worried about it. You probably did this, right? Short problem we just did. Okay. All right, all right, all right. Good, good, good. We good. That's fine. That's fine. Okay. So we will do that other problem tomorrow unless someone says, we got to do this today. Anybody? No? All right. So what we're going to do for the remainder of the time, how many of you got one of these things? I'm a player. I don't know if there's one seat in there or two, but just by looking at the shape of that car, the curves that it has on it, what do you suppose that is telling you? It is very fast. It is probably made of carbon fibers, so the weight of that is probably what? Really light. So we have a very strong motor pushing, I don't say pushing or pulling or engine, with a very light body on it, it's probably going to move pretty fast. In this video, they call it the ghost for a reason. Okay? So we will start that. We'll finish this. If we don't get done today, we'll finish tomorrow, and then we'll also do that story problem. And we'll be at the end of each one. All right.
Preparing to try to break the record of world's fastest production car. Set by the McLaren F1, this record has defied all takers for 7 years and stands at a blistering 240.3 miles per hour. A humid day and a tightly oval track seem to portend another failure. Ferrari is a circular track, so it kind of scrubs very low speed. You're constantly on a turn. But the Challenger is no ordinary car. It is with PSAUG from the innovative Koenigsegg Motor Company. It quickly accelerates past 100 miles per hour. And then 150. By the time the CCR is in sixth gear, it's well over 200 miles per hour, rapidly closing in on the old record. The man behind the new Challenger, Christian von Koenigsegg, had an infatuation with fast cars that began in his youth. When I was 5 5 years old, and so a Norwegian puppet movie about a bicycle return that would do himself a race car, and I was really excited by it. So I said to myself, that's what I want to do. I want to do my own car. Their dream led Christian to start the Koenigsegg Automotive Company in 1995. Soon thereafter, he designed the CCR. I basically started on a blank sheet of paper, and I had some ideas of what my car would be like. It was going to be a new, lightweight, high-performance sports car with a detachable hardtop that actually gave an invertible feeling when you take it off. CCR stands for Competition Coupe Radical. This CCR is the lightest, most powerful, fastest car ever built. It's the race car for the world. It has the features that you expect from a road car, such as air conditioning, stereo, power windows, power steering, etc. It's not racing car performance, but it's still very streetable and drivable, and you can cruise around with it. Our production facility used to be at my just quarter. Now it's the fastest car in the world in here. Under that car's sleek hood is an engine that holds the world's record for sheer power. This is the engine for the CCR. It's the most powerful production engine in the world with 803 horsepower. The CCR features a very lightweight V8 engine with a patented supercharging system. We based it on the production racing block. All the internals are our own engineering. We were looking at doing V12 and quickly realized that our performance target of 800 horsepower could be obtained safely within a V8 structure. One of the CCR's most striking features is its unique door mechanism. It has a very wide car and very wide doors. So we realized that when we parked next to other cars, that was not very practical. And I had seen on an electrical car in Sweden a similar door system where you open first outwards and then upwards, which was quite intriguing. But it wasn't really practical to first move out and then up. So we came up with this system where we did all in one motion, which, according to everyone we talked to, was impossible. It's probably the most difficult door system of any car in the history of cars. But it works very, very good and it's very, very stable. Another feature crucial to the car's success is much less obvious. There's precious little metal used in construction of the CCR. Instead, super high-tech carbon fiber makes up much of the car. The carbon fiber technology was originally invented by NASA in the US for their space program. Basically, it's the strongest, lightest, commercially available material to produce products out of. And it's still very, very expensive, but if you want to go lightweight and strong, carbon fiber is the way to go. In its original state, carbon fiber looks like the thin neoprene rubber used in wetsuits. The fiber is formed under molds of the specific car part it's to become. Then, on those molds, the parts are placed into a kiln-like oven, whose temperature is constantly monitored. This is the oven we use to cure our products in. We cure them for 120 degrees for 1 hour. Then it will be several more times stiffer than steel. The now super hardened fiber remains remarkably lightweight. The molded pieces are then fitted together by hand. We use carbon fiber almost everywhere in the cars, so that means the chassis structure is actually carbon fiber. The engine structures, even the valve covers, are carbon fiber. All the interior trim panels are very, very thin carbon fiber. Even the body panel system is carbon fiber. When you see them painted, they just look like steel or aluminum, but it's carbon fiber. Technology this sophisticated wasn't even imaginable when automobiles made their first appearance in 1886. Built by Carl Benz, the first production car had 3 wheels and 1 cylinder. It'll do about 12 miles an hour, 13 miles an hour. But a horse would have to really be pushing it to go 14 miles in an hour. And so it was quite a bit. He built 10 of them. I wasn't there, but I guarantee you Two of those cars went off against each other in a race. By the turn of the century, automobile speeds had increased enough to spawn the first sanctioned car races, including one in Grosse Pointe, Michigan, that carried historic implications. The Ford against the Winston, and this was back in 1903, and there was a prize of $10,000. Now, Ford had gone bankrupt a couple of times, but he built this car for this race. The Winston had mechanical trouble on the ninth lap and did not finish, and here comes Ford, goes on by and wins the race, and that was the start of the Ford Motor Company. $10,000 in 1903 was a lot of money, and he took that money and he started building his first Model Ts, and the rest is history. Ford's Model T came off the production line with a top speed of 45 miles per hour, an increase of nearly 400% over Benz's first models just 20 years earlier. But Ford soon had serious competition in the speed department. Among the fastest production cars of the teens was the aptly named Raceabout, built by the Mercer Automobile Company in Hamilton, New Jersey. They were two-seater cars, what today would be considered a sports car, although you sat on the body, not in the body, and they were considered stylish, fast automobiles. We have a 1912 Mercer in our collection, and that car will do an honest 95 miles an hour. We're talking almost 100 years ago. That was supersonic for its age. But it wouldn't be until the early 1930s that a production car would smash through 100 miles per hour. The Duesenberg. Duesenberg was actually a race car builder, and he raced in Indianapolis. Duesenbergs, they would go, in the second year, they'd do 90 miles an hour. And top year, they were good for maybe 105 miles an hour. Now, they only made a little over 500 Duesenbergs altogether between 1930 and 1936, but that was considered a very, very fast production car. The decade before World War II saw technical advancements like the Buick Dynaflash V8 engine. These powerhouses helped keep the speed crown in the U.S. with cars like the Buick Century. But after the war, European automakers made a determined run at the title, starting with a small but powerful two-seater from the UK that pushed the mark even higher. They decided to designate the car the XK120 based on the fact that it would go 120 miles an hour. And Jaguar's done that through the years. The XK120 and the ensuing E-Class of Jaguar Roadsters changed the world's perception of what a fast street car looked like. Still, other European designers like Enzo Ferrari began production models based on racing success. Ferrari's full emphasis for himself was racing, but to finance race cars, he built production automobiles. We're talking cars that you and I could get in, hit the key, start up, turn the radio on, well, listen to music. By the late 1960s, other European builders upped the ante, attacking the 200-mile-an-hour barrier, like one Ferruccio Lamborghini. Lamborghini was a farm implement manufacturer, and he was a very wealthy man. So he went back to his plant. He said, all right, we're going to build a sports car, and we're going to go head-to-head with Ferrari. And he did the Countach. The Countach was a absolute knock your socks off, you know, you just can't believe it, you know, take your breath away type of car. It was so revolutionary. And they claimed they were the first production cars with 200 miles an hour. Soon other cars were challenging even higher speeds. As before, most had their origins on the track. McLaren is a race car company. Louis McLaren was a race car driver, an Australian. He came to Europe and was driving for other people, and then decided to design and build his own cars. And they thought that it would be a great idea with all this technology they had, particularly from Formula One, to build a car for the street. The McLaren F1 became one of the most celebrated production cars ever created. Featuring a unique driver-center cockpit, it had a powerful BMW V12 engine that cranked out 627 horsepower. Introduced in 1991, the F1 went on to set the world production speed record, just over 240 miles per hour, on March 31st, 1998, only 2 months before the final F1 rolled out of the factory. But on that lucky Italian day in February 2005, After 7 years, that mark was about to become history. The 26 TCR ran smooth and hot. It powered up to 240 and then smashed through with a sizzling record-breaking 241 miles per hour, making it the new world's fastest production car. Of course, because the TCR is a production model, anyone can place an order. But you better start saving now. The basic price in US dollars with current exchange rate would be around $590,000 US, so it's quite high. But for that price, you get to drive a technological wonder. The world record-holding TCR, fondly referred to as the Ghost. We have a special symbol for the TCR, it's the Ghost. The Ghost version is sort of like